moving up from the TTY or interactive type terminal, we can see terminals that transmit their data in a burst mode, where the screen is formatted with information, the operator types information into the formatted screen, hits a transmit key, and the information is sent in a burst down to the computer. We also see cases where multiple terminals will share the line, either by multi-dropping the line or through the use of a controller that stores and buffers the information and sends it to the computer in a burst. We're going to take a look first at this formatted type terminal that sends that information up in a burst over a single line. With the type of connection we're going to look at now, we have a single terminal in a computer, and the terminal is going to work in a block or burst transmission mode, and we refer to this as point-to-point communications because there's only 2 points in the communications link. When we look at the point-to-point type connection with the terminal and the computer, there's a few rules we have to follow in sending information back and forth. First, the terminal, if it wants to send data when the transmit key is pressed, will send a message up asking the computer if it can use the line. The computer will then respond and say, yes, go ahead. The terminal will send the data up, and then the computer is going to respond with a message saying, I got the data okay. So there's a couple steps there. Can I use the line? Ask for the permission, and once the data is sent, you get back an acknowledgement saying the data was good or the data was bad, please resend it. Now we're going to take a look at a flow chart of the ANSI protocol for point-to-point connections and see how the information flows. Here we're showing a chart of the point-to-point protocol under the ANSI standard, or the American National Standards Institute standard for point-to-point communications. What happens is, when the terminal here wants to communicate with the computer, the operator presses the transmit key. The first thing that happens is an enquiry character, or ENQ, goes down the circuit and makes a bid for the line. If the computer is going to allow the terminal to transmit, it will return an acknowledgement or ACK character saying go ahead. The terminal will then send its data in a stream with the data bracketed by an STX at the beginning for start of text saying this is the beginning of my information, to an ETX or end of text at the end, followed by a block check character or BCC. Now the block check character is not a character on the ASCII chart. Instead, it's a sum of all the bits in the message. When this computer receives the information, it will check the parity on the data, and then we'll check the block check character for the proper sum, and if everything is good, we'll send an acknowledgement back saying, I got your data correctly. The terminal will then send an EOT or end of transmission saying, I'm all through with the circuit. This bidding and turning the circuit over is called contention, because the first guy of the two on the circuit that makes the bid gets the circuit. So they contend to see who can use it first. Now when we look at the point-to-point protocol, it was good where you had two devices talking to each other over one line. If we had a circuit like this where there were 4 terminals sharing it and talking to one computer, there needs to be a way to let you know which one sent the data in, and when the computer sends information back, how do you know which one to send it to? Here we show the 4 terminals each have a single character address identifying them. Whenever they send the data in, they'll identify the data with their address, and whenever the computer sends information back, it will precede it by the address so that the proper terminal can read it off the line. We're going to talk about the concept of polling, which is how we go out and collect data from terminals on a multi-point circuit or multi-point line. Now in polling, what will happen is the computer system will send a message out to each terminal in sequence and say, do you have data, do you have data, do you have data? Until it hits a terminal that has information, at which time that terminal will respond by sending the information back in a burst. When the computer has information to go out to a terminal, it will do the opposite function where it'll send out a message selecting saying, can you receive data from me? If the terminal says yes, he'll send the data out. So we'll look at polling first, which is collecting data from the terminals, and selecting, which is sending data back out. In the polling or multi-point protocol, the computer is usually designated as what's called the master station. It has control of this circuit. The terminals are designated as what's called slave or tributary stations. They can only respond when they're addressed by the computer. Usually the computer sends out a poll message which is seen by all of the stations. In this particular case, though, the poll message is addressed to station B. Station B receiving the message will then respond. In this case, it's responding no data or I don't have anything to send. The computer will then go on and poll another station on the circuit, such as station C, and it will respond with either a message or no data. Now, on the polling circuit, the poll message, remember, is seen by all of the stations, but only the addressed one responds. This is a copy of the chart for the ANSI protocol for polling. In this particular case, we have a 5-character message which goes out from the computer polling the remote station. The message begins with an EOT and has a 2-character station address, a lowercase p to indicate it's polling, followed by an ENQ. When this message goes out, if the station AA did not have anything to send back, it would send an EOT saying, I have no traffic. When the EOT comes back, the computer would now change the address and poll the next station in sequence. If it polled station AA and there was a message to send back, station AA would respond in this way with a message that said, start of header, the header being information that precedes the data, which in this case is the address of the terminal responding, followed by start of text, the information, the end of text, and a block check character again. Now the polled station sends its own address back with the information so that the computer knows which station the data came from. Now usually you can assume that the address in the poll message would tell you who you polled, but because the data may move around in the computer, they add the address on so that you'll know as the data moves through the computer who to send the answers back to. When the computer receives the message, it will send an acknowledgement saying that the parity and the block check were okay, and the terminal will respond EOT, and we return to polling again. Now, if it's possible that when the message was sent in, there was a parity error, the computer would send a NAC, or negative acknowledgement, and the terminal would retransmit the message. Polling allows the terminals then to share one line, or one communication circuit. Also, within the polling protocol, if you notice, there was a loop where we went down. If the message was wrong, we sent a NAC, or negative acknowledgement, which said retransmit the message. If you get into that loop and the message is constantly in error, you would normally stay in that loop, except the protocol says if you retransmit a certain number of times, you just give up and go on to the next station. That keeps you from locking up the communication circuit because one terminal's gone bad on you. Now, in addition, there's the thing about timeouts. If you send a poll message or some other response to a terminal and it does not respond to you, the protocol says after a certain amount of time, which is usually set by the computer manufacturer or the software vendor on the computer, you will give up and try again or go on to another station. So remember, retransmits and timeouts are controlled by the software or the computer vendor. We just looked at polling, which was the method of collecting the data from the terminal. In one particular case, you may have entered a request for information from the computer. Now the request has been processed and the computer has to send information out to your terminal. What we're going to do is we're going to look at selecting, which is the process of sending information out in response to what the terminal sent in. And the information coming out may be displayed on your terminal, or it may be a report going to a printer in your local area. In the select portion of the protocol, the computer sends out a message that's almost identical to the poll message, except it has a lowercase q replacing the lowercase p. The lowercase q says that this is a select message where the computer wants to send you data. The terminal will respond ACK or acknowledge if it's ready, and the computer will send the message down. And the message is bracketed again: start a header, station address, start a text, data, end a text, and block check. If the data is received correctly at the terminal, it will send an acknowledgement back, and the computer can return to either polling or selecting other stations. If, when the computer sent the select message out, the terminal for some reason was not ready to receive information, it would send a NAC or negative acknowledgement saying, don't send me data, I'm not ready. If after it was ready and it got the acknowledge and the data was sent, the data was received incorrectly at the terminal, it would send a NAC or negative acknowledgement saying, I received the data incorrectly, and the computer would resend the data. Again, the number of times the data was resent would be determined by the computer and the software. There are variations to the standard protocol of just polling and selecting. If we look at this network here, we see a computer with a data link that goes out, and in this case we have 3 terminals that are hooked to what's called a controller. In this case, terminals AB, AC, and AD are connected to controller A, which corresponds to the first character of their address. When the computer wants to poll, instead of polling each terminal, it polls the controller. And the controller determines who has data to send and will send it on into the computer. Or we may have a case here where we have terminals daisy-chained or connected together, and we poll one of the terminals in the daisy chain and it answers for the rest of them, or tells them when they're polled and they can send data on. In this way, rather than polling each individual device, we're polling groups of devices on the line, and this is called group polling. We can also do group selecting, where we have a message that we want all of these terminals to see, so we send it down the line to the group and it displays on all of the terminals. Or we can send a broadcast message which will display everywhere on this network or line. So the broadcast will display everywhere. The group select will display only on the group. Now finally, because polling does utilize a lot of the time on the line and takes computer power and resources, we can take and put the line to sleep and not poll. If we poll the circuit a couple times and nobody has traffic, the computer can send out a message that says, I'm dropping out of the polling mode and going to contention. At this point, the computer waits and no longer polls the line. When somebody on the circuit has a message to send, he will send a contention in, which will wake the computer up, and the computer will begin polling. On some systems, by not polling when there's no traffic, you can save a lot of time in your software. As the protocols become more and more complex, the amount of time we spend transmitting the data becomes critical. Here, we're looking at the character A in the ASCII code as it would be sent down the line asynchronously. Now, if we look at this, we have a start and a stop bit to tell us where the character begins and ends. This makes a 10-bit character. Now, using a 1200 bit per second modem, it means we can only send 120 characters per second. If we could eliminate these 2 bits and make it an 8-bit character and send just the data without start and stop, we could send 150 characters in 1 second. What we want to do now is look at a method of changing our data transmission, so instead of telling the beginning and end of each character, we're going to tell you the beginning and end of the data streams. Now remember, we've gone to more complex protocols where we poll and select, or we're in point-to-point contention mode, and we send data in streams anyway, so why bother to tell the beginning of every character? Why not tell the beginning and end of a complete message? This would represent a data stream that came down from the computer and did not have any start and stop bits in front of the information. Now the way the computer would pick it out would be through the use of a character called sync, which stands for synchronization. The computer knows what the sync character looks like, and here's our sync character on the line below. As the data is coming in, the computer counts off every 8 bits and compares it against the known sync character. If the first 8 bits doesn't look correct, the computer moves one time frame and tries again. As it's going along sampling the data line, eventually it will see an incoming sync character, and here we have it. Our sync character in memory matches up with the one coming down the line. At this point we know we've found what's effectively the start. But the computer then takes and counts off 8 bit times after that and looks for a second sync character. So it must see 2 sync characters in a row. If it sees 2 in a row, it says, I have achieved synchronization. I found the start of the message. From then on in, every 8 bit times after those 2 sync characters is 1 character in the message. Reviewing the procedure once again using the wooden blocks, what we see is the sync character here in the computer is compared at each bit time to the incoming data stream. Finally, when the incoming data stream, the 8 bits, match what is in the computer's memory, we take this out and say we have achieved the first sync character. Then the computer waits and counts 8 bit times without looking at the line and compares again. At that time, it should see the second sync character. At that point, it says, I've seen 2 sync characters in a row. I have synchronization. If I count off every 8 bits afterward, what I will see is an individual character. And if you look at this character here, you'll see that in the ASCII chart, a 1 followed by 7 zeros is the code for the ASCII character start of header. So that's the beginning of our message. In most cases, changing the communications from asynchronous to synchronous is simply a matter of adding sync characters in front of every portion of the message sent. For instance, here in the point-to-point protocol, instead of sending just an ENQ, we would send a series of sync characters followed by ENQ, and the response would come back with a series of sync characters followed by an acknowledgement. The same thing would hold true whether it was the polling protocol or the contention protocol. Simply adding the sync characters will change it from async to synchronous protocol. The last thing to notice about the synchronous transmission is what we call the timing. When you send data asynchronously, the start bit tells you the beginning of the character, and then the computer counts off the time in bits per second. So if it's a 1200 bit per second data transmission, it means every 833 microseconds another bit is coming along. In a short character, it's no problem because you can time for 10 bit times and collect the data. If you get into synchronous transmission where you're sending a message that may be 4,000 or 5,000 bits long, it means the computer must maintain a very close timing over the transmission of the 4,000 bits. This equates to an error of about 0.01 of 1% in the clocking of the data. Now, we get around the problem by getting clock from the modem. And if you remember from our discussion of modems, the synchronous type modems, which were the phase modulated ones, generate a clock, send it over the line with the information, and then recover the clock so that the computer doesn't have to worry about the timing of the bits. The modem tells it when the next bit is coming out so it can maintain synchronization once it's seen the sync characters. Let's review the modem timing circuits. Reviewing our modem clock circuits, we see that the modulator or transmitter, as it's sending the data, gets clock from the modem itself. The same clock is also given to the transmitting device to tell it when to send the bits into the modulator. At the receiving side, the demodulator takes the information in, decodes the phase shifts, and generates a new clock which is given to the receiving unit to tell the receiving unit when the bits are coming out here on pin 3 of the EIA interface. In this way, the modem will ensure that the receiver always knows when the next bit is present and keeps it in time with the bits. All the computer has to worry about is counting each 8 bits to rebuild the characters. Up till now, the protocols we've looked at are what we call byte-oriented protocols. In other words, all the information in the protocol, even the framing characters such as start of text and end of text, consist of 8 data bits or 1 byte. Now, computers internally also run on 8 data bits or 1 byte. You can have a problem where if you were going to move a computer program over a transmission circuit to another computer, the information within the program can look like the control characters. In other words, let's say I had a computer program that did data transmission and I wanted to move a copy to another computer. Somewhere in that program is start of text and end of text characters. These characters could cause the frame of data being sent to terminate at the wrong place at the receiver. So we have to have a way of sending information transparently. Now, one way to do this was what was called transparent synchronous communications, where they used a character in pairs, and they said whenever you wanted to send an end of text that was a real end of text, you would send a character like DLE followed by end of text. This was cumbersome because if you had repetitive characters, you were sending 2 characters for every one, and you filled out the frame with a lot of extraneous data. Modern computers are now using what we call bit-oriented protocols, in where they tell the information and the framing according to positions of the data within the data stream. In our bit-oriented protocols, as we call them, because we're no longer dependent on characters now to frame our transmission, but bits, what we see is there's a character called a flag, which is unique. It cannot occur anywhere else but at the beginning or end of a message. The flag character says, okay, this is the beginning. The first thing following it will be a header. This header will tell you the length in bytes of the data. Now, since you know the length in bytes, you can just count the data off and you don't have to look for an end of text. And at the end will be your block check, or what they're going to call a redundancy check character, and a final flag. In this way now, the data within this block can be anything you want, and it will not interfere with the transmission. First, let's look at the frame, and then I'm going to show you how the flag is kept from occurring in data. In our bit-oriented protocol, this would be a typical frame of data being sent down the line. First would be the flag character, which is 8 bits long, followed by an address. Now, in point-to-point, you may not see an address, but in multi-point, same thing happens as in our byte protocols. There's an address to tell who the message is for or from, followed by some control information. In the control information is a number which tells you how long the data field is. So we specify the length of the data, and then we don't need an end of text, followed by what they call the CRC, cyclical redundancy check, which is a more comprehensive version of the block check character. And we end the frame with a flag character. So this frame corresponds to the same type of data frame you would see in the byte-oriented protocols. The only difference is it has flags instead of sync characters, and it has a control field to tell you how long the data is. The flag character has the pattern of a 0, 6 ones, and a 0. Now, this is reserved, like we say, for the flag on the communications circuit. If you're transmitting data and during the data a flag character should occur, the communications hardware will get around it by stuffing an extra bit in to make it look not like a flag character. For instance, as the data is going out on the line, the communications hardware is watching it. Whenever it counts 5 ones in a row, it automatically says, this could be a flag character, and stuffs a 0 in. At the receiving end, whenever hardware sees 5 ones followed by a 0, it throws the 0 away. In this way, within the data stream, you will never get the flag character on the line. As the flag character starts to occur, a 0 will be stuffed, and at the receiving end, the 0 will always be taken out. Now, even if this had been a 1 down here at the end, as long as there were 5 ones in a row, the 0 would have been stuffed and taken out. In this way, we reserve this pattern to always show synchronization on the communication circuit. The bit-oriented protocols are seen in things like IBM's SDLC, or Synchronous Data Link Control, which is the protocol under their SNA, or Systems Network Architecture. Most manufacturers now are moving towards bit-oriented protocols, which give them more control and better throughput on communications links. Reviewing Section 3, the first thing we studied was about modems and the communications circuits. We looked at how modems convert the digital signal here at the RS-232 interface into tones or other analog signals to send them over the communications circuit. Next, we looked at the computer terminals and the computers and how they communicated using a protocol across the circuit provided by the modems and the communications line. This concludes Section 3 of our course on Introduction to Telecommunications. In Section 3, we went over communications equipment for data. We looked at modems, computer terminals, and the protocols that make them talk. Now you should sit down and look at the exam and review the terminology at the end of this chapter. If you're having any problems, try to go back through the video and follow along in your textbook. Following are the terms to review for Section 3. AM, amplitude modulation, ASCII, asynchronous, bandpass, bit protocol, block mode, byte protocol, carrier, CCITT, clock, controller, DCE, demodulator, digital, DTE, EIA interface, I pattern, flag, frequency modulation, FM, FSK, in phase, interactive terminal, master station, modem, modulator, out of phase, parity, phase jitter, point-to-point, polling, PSK, QAM, retransmission, RS-232 V24, selecting, sine wave, slave or tributary, start bit, stop bit, synchronous, terminal, timeout, and TTY. Welcome to Section 4. In the first 3 parts of this course, we went over with you the various types of equipment used for both voice and data communications. What we're going to do in Section 4 is we're going to show you how this equipment is put together to form networks and where you acquire the equipment to make those networks function. The most important problem facing us nowadays is what we call regulation and deregulation. In the 1960s, you bought all of your communications equipment from the telephone company, right up to and including the modem. In the 70s, we were allowed to buy modems and hook them up to telephone company circuits. Finally, in the 80s, we were allowed not only to purchase our own modems, PBXs, telephones, but we were able to go to separate companies to buy telephone service. In other words, not only the Bell system could provide long distance as an example, but MCI and Sprint could provide the service. So services and equipment became deregulated, but there are still dividing lines as to who is allowed to provide what service. When the telephone companies were deregulated, the Federal Communications Commission, which sets our nationwide laws on how phone companies are controlled, divided geographical areas up into the LATAs, or local access and transport areas. Within this area, the telephone service was still provided by the local telephone company. And if you made a call from a telephone within that LATA to another one, the call was handled by the local phone companies. If, however, you wanted to call from your LATA to a telephone within another LATA, when you dialed the long distance number, your call went to the central office that you were connected to, and then was connected to a central office for what was called the inter-LATA carrier. This central office is referred to as a POP, or point of presence. The call goes over the inter-LATA carrier to their point of presence in the other LATA, and then is sent down to the central office where the phone rings. This interLATA carrier is in competition with other carriers. You select your long-distance company from a list like MCI, Sprint, and AT&T. They're called OCCs or other common carriers. They carry the calls between the LATAs. So we have competition if the call moves between two of these LATAs, but nothing within the LATA. All of that must still be provided by the local phone company. Looking again at the interLATA carriers, or the long-distance carriers, each of them has central offices within each LATA where the calls are passed to by the local telephone company. These central offices, again, are called POPs, or point of presence. The same holds true now for leased lines or private circuits. If you want a circuit between the LATAs, you rent it from one of the long-distance carriers. If you want a circuit within the LATA, you rent it from the local operating or telephone company. The interstate or interLATA carriers operate in this sort of a gray area of a deregulated environment. The telephone companies are regulated by either the FCC or the State Public Utilities Commission in your state. The long-distance carriers are regulated, but their prices are allowed to vary, and the services they offer. So you can go to different long-distance carriers and get different types of service. When you choose a long-distance carrier to handle your traffic, what you'll find out is the way they've written their tariffs, which are what we call the pricing structures that they file, vary. Although one may appear cheaper than the other, in looking closer you may find out that the discounts are outside of normal business hours. Or you may find out that one's tariff does not have the same business hours as another one. In some cases, you may have a really high discounted carrier which only serves a couple of states in your geographical area. So deciding on which of these long-distance carriers to take can be a real problem for communications managers nowadays. What you have to do is look at the tariff and compare it against the services you require for your area. The next area that's deregulated in the telephone network nowadays is the customer premise equipment. Now, if we look at the phone company here, we see that they own the switching equipment and the distribution, which includes the cable that goes under the street called the outside cable and ends up at your house or business office. Now, right here where the cable enters your building is what's called the demarc, or the line of demarcation. Everything on this side of the demarc belongs to the telephone company, and you rent it from them on a monthly basis. Everything from this side of the line over belongs to you, and you either rent it from another vendor or purchase it. Now, in some cases, this equipment may be rented from the local phone company, but it will be through a non-regulated subsidiary, not the phone company itself. In here, you can now buy your own telephones or your own PBX and have them installed and maintained by your own personnel. We refer to this equipment as Customer Premise Equipment, or CPE. CPE is totally deregulated now, except the equipment that actually connects to the telephone line must be approved by the Federal Communications Commission, or what we call the FCC. Here at Spectrophysics, we're looking at the building access facilities. These pipes run back out to the street, and there where, in this local area, Bell System brings in their cables to supply the telephone lines to Spectrophysics. Now, not all the pipes are in use, and in some cases, like here, they've left a pull cable made out of a nylon rope that allows them to pull in extra cable. Since these two cables did not use the entire diameter of the pipe, by pulling in a nylon rope like this with the two cables, it enables them to pull in additional facilities at a later date. The building access conduit here comes from the other buildings on this campus, and there are approximately 5 other buildings. So the telephone lines come in from here, go into the PBX, and then the outgoing station lines to the other buildings come through these cables going back out. Now here, our telephone cable, which comes from the phone company, is brought into a splicing case. Now, since the cable is really dead-ended and cut off, the wires have to be spliced and brought through here to what we call the station protectors. These are, in effect, each one of these screws has underneath it a fuse. And what happens is any electrical discharge outside the system, such as lightning or other high voltage that may cross into these lines, will cause the fuse to blow here and protect the telephone system in the building. Also, any high voltage that may cross into our telephone lines in the building could blow the fuse to prevent the voltage from feeding back to the central office and harming the telephone company equipment. Now, when these facilities were brought in, the telephone company at a later time brought in some new digital facilities, which are brought over here and terminated in a more modern type of station protector, which takes up less room than this large assembly here. Regulation of the phone companies and the various common carriers is handled by one of two organizations. In the first case, if it's an interstate carrier, which means crosses state lines, the FCC regulates them. And in the case of MCI, Sprint, or AT&T, any of their services that cross state borders are filed and approved through the FCC. The FCC also handles equipment registration. In other words, getting a telephone or other device registered so it is allowed to be connected to the public telephone network. You submit it to the FCC to get the equipment registration. Now, the PUC, or Public Utilities Commission, in each state handles who can provide the inter- and intra-LATA services. Now, in some cases, you take AT&T may provide interstate services, which are FCC approved, and then may provide inter-LATA services, which do not cross state lines, which have to be approved by the local PUC in that state. The PUC also regulates the local phone company for their intra-LATA service and for their local access fees. And the local access fees being the amount of money you pay per month to get a telephone line into the central office to make and receive telephone calls. Now, the PUC may not be the name of the regulatory commission in your particular state, but it's pretty generic. Here in California, it's called the California Public Utilities Commission, or CPUC. When you leave this course and go out into the real world of data communications, you're going to see equipment that will be a little bit different from what we've shown you now so far in the tape and in the book. You're going to see your terminals, controllers, and mainframes with things like what are called front-end processors. Now, what we want to do is tie those together for you into a general overall view, and then you can go out and look at the equipment in your own office to see how similar or dissimilar it is. Looking in your office, the communications may take place using a terminal or even a personal computer with a program to look like a terminal, connected through a modem, or you may have multiple terminals and a printer connected to what's called a remote controller. The controller would then be connected to the modem. At the computer site, the communications link may come directly into the computer, or if it's a very large system, it may have what's called a front-end processor. All the communication software would run in the front-end processor. It would handle polling and talking to the terminals and pass only data over to the computer for processing. So you may see a front-end processor or a direct link into the computer. This is the IBM Cluster Controller. This is a model 3274. To this cluster controller, the various IBM 3270 type terminals and or printers are connected via coaxial cable. This cluster controller is then connected via this modem into an IBM mainframe. The connections for the terminals are in the back of this unit, and the coaxial cable used to connect up the devices is like this with a BNC twist lock type connector. This is an IBM 3705 communications controller or front-end processor. The 3705 takes care of communications functions such as polling and data translation. The 3705 passes the incoming data from the communications lines to the IBM mainframe. This concludes section 4 of our training course. Now what you should do is go back and review section 4 to see if you've got the basic ideas, and do the examination at the end of the chapter. If you have any problems, go back and follow through Section 4 in the book while you watch the videotape. Following are the terms to review for Section 4. Communications Controller, Customer Premise Equipment, DMARC, Deregulation, Federal Communications Commission, Front-End Processor, Interlata Carrier, OCC, Outside Cable, and Public Utilities Commission. This concludes the Information Factory's course on Introduction to Telecommunications. This course was designed to give you an overview of the basic concepts and ideas of voice and data communications. If you want to proceed further, we recommend that you pick up our courses Voice Communications 1 and Data Communications 1. With this changing technology, we recommend that all personnel learn both voice and data communications. On behalf of myself and John Stanley, we'd like to thank you for viewing our course Introduction to Telecommunications. We also hope that you'll look at our catalog and keep in touch with the Information Factory as we produce new courses on digital transmission, local area networks, and other items of interest to telecommunications personnel.